Good morning, everybody. I present this work that is a joint collaboration with my advisor, Sergei Goninsky, and the help of Farzad and Christian from Klagenfurt University. Adaptive bitrate video streaming is a prominent application in internet in terms of traffic. And how does it work? We have a video that is stored inside a server, and this video is not stored as one file, but is partitioned in different chunks. And these chunks are encoded at different quality level. To higher quality is associated also a bigger dimension of the chunk. Then the client strives to download these chunks in order to show a video to the user. And the client, by a so-called adaptive bitrate algorithm, decide which quality of the next chunk he has to download. Unfortunately, this ABR algorithm can make mistakes. Indeed, I have represented here two possible mistakes that he can do. So, for example, he can underestimate the bandwidth, and so he will download a chunk at low quality while one of higher quality would have fitted better. Or what can happen is that it makes an overestimation of the bandwidth. So it will download a high quality chunk, but this chunk does not make in time to be downloaded. So what is the consequence of this is that the client will see his video freezing. Everybody of us actually have experience of this. And this freezing is called in our jargon stall. Why ABR does all of that? Because it wants to maximize the final satisfaction of the user from the video streaming session that is watching. And what I just said is the definition of quality of experience, which indeed is this metric that measures the satisfaction of the user. Now, as you may think, satisfaction is quite a subjective concept. So how can we measure it? Well, the most straightforward way is by using subjective assessment. So you show an experience, a video streaming experience to a user, which in return gives a feedback through a proper interface. In this case, I've represented a slider. And for the sake of clarity, I will define the experience in this paper and for this talk as a series of chunks characterized by some objective influence factor, which are variables, literally variables, that describe this experience by perception. These influence factors are a lot in literature, but for example, just to make you understand, one of them is the stall duration that I mentioned before, or for example, the image quality of each chunk. Now, as you know, real video streaming setting doesn't work in this way, right? Because when you see a video, you are not requested to give back a feedback of how much you are satisfied. What actually happens in subjective assessment is that the experience is shown to a group of users that we will call raters. They score the experience, and this experience is that these scores are then averaged into a new metric called MOS, which, and I want to highlight this, represents an hypothetical average user. What we see here is just a piece of the total subjective assessment framework, where in input we have a big set of experiences, then a sampler, which is basically a researcher or the guy that set up the subjective assessment, select a subset of them, and they are iteratively shown to the raters. Then the MOSIS and the influence factor all together are used by a modeler to build a so-called QE model. The modeler is, for the majority of time, just a regression function. And the outcome of this subjective assessment is a QE model, which is the tool that is actually used for measure the satisfaction of the user. Instead of asking him to give me the feedback, no, they use the QE model directly. Indeed, this model is then embedded inside a ABR streaming system. Famous example of ABR streaming system that use QE model are MPC or Pensive, that also have been mentioned in the keynote talk. And then the video are crafted, generated based on this QE model, and they are watched by a lot of viewers. Now, What is important to notice here? Well, first of all, the viewer, the consumer, basically, us are, I don't know, million probably, but the model is constructed by just few people, few raters. Moreover, the QE model by per se is not representing not even the raters because it's an average. So it represents an hypothetical average user. Next question is, can this model built in this way, this QE model, be accurate for all the viewer? So in this slide, we are representing the scores distribution of 32 users from Waterloo 4 dataset, represented as boxes, and we have highlighted in green the average rater. As we can see, the scores distribution of the viewer is quite distant, quite different from the one of the average rater. Moreover, in this paper, we defined as a typical viewer the 10% that are furthest from the median QE perception. 10% is not absolutely a hard threshold, but it's just arbitrarily chosen by us. But it's in essence, these atypical viewers are the ones that are the most misrepresented by the average rater. So in conclusion, this QE model built in this way is inaccurate for a typical viewer. And how can we cope with this problem? Well, one solution is to build personalized QE models. And actually, there are various options that we can follow for doing that. For example, we can use indirect feedback from the viewer, so we are inferring their QE by monitoring their behavior. Or we can use multiple reference group, where we associate a viewer with a smaller set of raters with similar taste. Or we can let the viewer to tune its own QE model. We considered all these possible options, but since they have been too complex or they do not lead enough accuracy, we have discarded them. So all in all, given this consideration, we came up with some requirements that we want from a solution. And so we want that the viewer that enjoyed the video session is also the one participating in its QE model building through a feedback. And we want this feedback to be explicit, expressible, and actionable. In one sentence, the viewer is the sole rater for the personalized model. So now this viewer actually is participating in a subjective assessment because he participates in the QE model build. So he gives score, gives feedback to experiences. And the question is, but is this feasible in a reasonable amount of time? I mean, how much effort are we asking from the viewer? This is what have driven our work. So we came up with our methodology called individualized QoE, which essentially is a new methodology for building personalized QE model requiring low effort from the viewer. How? By limiting the number of the subjective tests, the experiences to be scored by a small number, and how, even though giving a super high accuracy to the final model, and it achieves that by using an active learning framework, which adopt a new sampler and new design modeler. We call them random improved greedy sampling for the sampler and extended support vector regression for the modeler. Here, I'm depicting an overview of our solution, but in its essence, the sampler and the modeler iteratively interact with a viewer in the loop that gives the score to these experiences, and iteration by iteration, the modeler improves its performance. Now, I want to spend more time in explaining you how we design our sampler and our modeler. More specifically, I will guide you through the logical step that we follow for reaching our final design for the sampler. So, in this slide, we are depicting 315 experiences taken from Waterloo 4 dataset. These experiences are described by two influence factor, the total stall duration and the image quality with values that are normalized between 0 and 1. And with symbols and colors, we are representing the score given by this user to these experiences. Green color represent higher scores and red color lower scores. Clearly, an experience with low stall and high image quality has more a score higher. What are we asking here is how can we select 50 out of these 315 experiences in such a way that these 50 experiences represented maximum the total number of experiences. Why we are doing that? Because this is a very important factor for giving a high accuracy to the final modeler. So one easy on the left side we have the same graph that you see before. Here is the case of the animation that is not working. One very easy possibility for selecting these 50 experiences is by taking them randomly. But unfortunately, as you can see, the experiences tend to be clustered along the axis, while in the middle, the space is quite empty. So random sampling is quick, but gives a very poor coverage of the influence factor space. How can we slightly improve this? We can use greedy sampling. In greedy sampling, distances into the influence factor space is taken into account. And so we can see that actually this is better in terms of coverage of the input space, but it has another problem. It is biased towards high scores because, as you can see, the green points are the majority. So in this case, we have a poor coverage of the output space, which is the score space. How can we improve this again? We can use improved greedy sampling, which consider distances into the influence factor space and also in the output space, the space of the scores. But we do not know in advance the scores that will be given by the user, right? So we need to infer them, and this is where the active learning part kicks in, because the modeler is used for inferring the output space in order to run the algorithm. Unfortunately, the modeler at the very beginning is not trained at all, so he's not very good in suggesting to the sampler which experience to pick. And unfortunately, this algorithm is also quite complex, so we can say that it has an high complexity with initial small gain. So our final design for our sampler is a combination of random sampling for the first 10 experiences and improved greedy sampling for the remaining 40, for a total of 50 experiences. Now, those numbers came up after experiments that we ran in the paper. Moving to the modeler part, we call our modeler XSVR because it's a support vector regression that uses 10 different influence factors. And we proved in our paper through permutation feature importance technique that all of them are useful for the performance of the modeler. Going back and putting all together, we have the same, we have the design that I already showed you before, but in this case, you notice that the viewer and the rater is the same person, the red guy, and the modeler created is adopted by the ABR streaming system and is used for craft the video to the very same viewer that participates in its QE model construction. We envision our methodology to be used on a voluntary basis, so people that actually don't want to use iQoE, they don't have to, because they can just use the general QE model that is already stored into the video streaming provider, and this is represented by the green guy. And moreover, we are expecting that the people that are the most incentivized to use our methodology are the atypical viewer, because they are the most misrepresented by the green model here. That's all for our design, and let's move to the evaluation part. So we develop iQoE inside a server and the viewers can interact with it by link, password, and username through which they can connect to our server. And to them are shown 120 video streaming experiences. Only 50 of them are used for training our iQoE technique, while the remaining part are used for the evaluation. All the experiences are 8 seconds long because they are composed by 4 chunks of 2 seconds. And in total, we have gathered 120 real viewers leveraging Microworkers platform. The viewer interacts with our server through the interface that I'm depicting there. So basically, they move the slider and click a button. So what do we evaluate? Well, we compare the accuracy of iQoE against traditional QE modeling. More specifically, we compare iQoE against 10 prominent QE models that span different possible designs. So we are going from exponential function to logarithmic to deep learning one. For example, B model, that the one that we call here B, is very popular in ABR video streaming settings because it's used by Pensive or MPC. And here we are depicting the distribution across all the 120 viewers of the mean average error, which measures the distance between the regression function and the ground truth data. We see clearly that the red line iQoE outperformed the others. Quantifying this better performance, we can state that the average MAE decreases at least by 42% for all the viewers and by 85% for atypical viewers. And how much time is requested to them for reaching these results? Well, the total playback time of our 50 experiences is 7 minutes. Then there are some extra time, like for example, downloading the video per se by itself takes time. Thinking about the score takes time. Maybe the viewer wants to take a break in between, so it takes time. So in total, we have estimated that the time needed in median is around 22 minutes, which we think is a reasonably low effort. This is our most important conclusion, but we extend our evaluation section by doing simulation, specifically for evaluating the design choices, parameter sensitivity, and the overhead of iQoE. And for doing this, we leveraged a new technique of synthetic profile, where we took 8 different trainable QE models and 32 sets of scores from real viewers. We trained the model with these scores of the viewer. In total, at the end, we had 256 synthetic raters, which are trained model. With them, we make them score a lot of experience quicker than real viewers. So in this slide is an example of sensitivity analysis that we conduct. So we fix the sampler and we change the modeler. So we are comparing SVR against random forest, extreme gradient boosting, and Gaussian process. And we see that across the number of experiences, the MAE of the iQoE is constantly outperforming the others. We run similar sensitivity analysis also for other alternative design, and the conclusion is always the same, that iQoE consistently outperform design alternative. Finally, in this slide, I'm showing you the per iteration time overhead of our solution, which in this case, this overhead is basically picking the experiences and training the model, removing all the time that the viewer wastes for think about the score and giving it. And what we want is that this time should be negligible, not perceived by the viewer itself. So even after 250 iterations, the total amount of time taken is around 0.15 seconds, which is negligible for the viewer. And we run a similar experiment also for the memory consumption, and we can conclude that the processing and memory overhead of iQoE is negligible. In conclusion, iQoE is a new methodology for building personalized QE model requiring low effort from the viewer. We evaluated it with 120 real viewers and extend the evaluation with simulation, and quantifying its improvement, it gives it gives an increase of accuracy of 42% for all the viewers, 85% for atypical viewers, requiring just 22 minutes of their time. That's all. Thanks for the attention.
Thank you. Any questions? Yes.
Support. That was fun.
Thanks.
Pity about the lack of animation. I actually just got methodology question, which is, so the Likert scales, that's the really bad, medium, kind of moderate, good, oh, well, awesome, those sort of scales that surveys use. There's a lot of literature to suggest never leave a middle. I was wondering if you had an histogram of what the humans actually responded over that scale and how that compared with the robots, because I'm wondering if you've trained something that robots like and you just found the robots really like it. Do you have any insight to the original data? And also, have you considered making the cognitive load for the humans much lower by simply offering two choices, good, bad, no middle, good, bad, and then do the analysis on the basis of only two responses? Because humans quite like pressing a button that says good or bad and don't have to pick a cognitive load slider. Oh, that was kind of good, I didn't really like it, etc.
So if I have understood well, the first question is if the synthetic raters are similar to the real raters.
Yeah. And with the real raters, was it a distribution or was it a skew?
Okay, actually, we did this and we compare. I have a slide somewhere in the backup slides. I don't know if I can show you this one. Actually, here we are comparing the real raters against the synthetic raters in terms of correlations. And we see that actually they are quite similar, very much similar, if this is your question.
Well, actually, let me chime in. I think Andrew asked a lot of questions in one.
No, the second one.
So I think about the distribution of scores, for example. So we actually did the evaluation on the scale from 1 to 100. Well, partly when we started, we used Waterloo data set, which already uses this scale. Actually, we have a paper coming up in CoNEXT' next month. So actually, we show that actually, indeed, if you plot the histograms, you have a spikes of the scores. The scores divisible by 5. For example, 50 is most popular. So indeed, so I think actually one conclusion from this, not this paper, but kind of the subsequent paper, that you should use relatively small number of scores. Well, actually, the common recommendation is 5, right? If you look about MOS scale, it's 5. So I think that's kind of a wisdom we got from there.
Yeah,
and I think
just for saying, 5 is not 2, as he was suggesting, right? Bad or good is maybe too simplistic. 100 is too much, probably. We have some insight on that.
And another thing you ask about, so again, most of the paper, most evaluation and the main results come from the studies with the real users. So the simulations in the second part is a kind of a supplement. And I think what you kind of anticipated is there as well. So if you look at the real scores, the error is much higher. So with the synthetic rates they are lower, which is also kind of what you, I think, implied in your question. So if you, create a synthetic user, then they become more predictable than the real users.
So thanks very much.
One last question.
I was wondering, did you consider audio quality as well? Because if you look now, so if you do streaming, audio comes in, let's say, 3 qualities, whereas if you stream, let's say, from YouTube, you have so many quality levels you can select from. True. And oftentimes you have stall, not because there is not enough video content, but you don't have enough audio content. Did you look at that?
No, we didn't consider the audio in this paper, just the video part.